quite a topic we just had, but we have something exciting for you coming up next. I'd like to pose a question to you all. Are you looking to have film quality stylized characters for your game? Well, I have Brian Anderson here who is going to say more. Take it away, Brian.
Much. Thank you. Hey, everybody. Yep, my name is Brian Anderson. Thanks for coming today. I'm a solutions engineer at Unity, but my background is in film production, and I worked as a character generalist and a character artist for almost 30 years now. So over that time, the industry has changed quite a bit, and the technology has changed too. So we're definitely in the age of real-time AI and machine learning now. So today, I'm going to talk a little bit about simulation for stylized characters. Now, this is a workflow demo, and we're going to be using Ziva's tools. And I'm showing it on a stylized character here, but you could apply these type of techniques to any kind of character. Machine learning is one of the key aspects of the talk. And Unity has a tool in beta right now called ZivaRT, which does the type of machine learning that I'm going to be talking about today. If you're curious about that, definitely hit me up after the session, or you can go over to the character booth and find out more about it. Yeah, so if you're not familiar with machine learning for character deformation, it's probably worth a quick primer. So we'll start off with a super simple example. If we take a character rig made in a traditional way, we run it through a machine learning process to learn those deformations. That same character rig is going to evaluate faster in the end. So why is that? So our character rig is made up of a lot of different things, but two of the main components are the joint hierarchy in the balanced skin and the deformation corrections. And it's typically those deformation corrections that are going to be slow with our character rig. And those deformations could be made up of all kinds of different things. It could be custom deformers, it could be hand-sculpted correctives, it could be a helper joint system with a lot of different behaviors to help maintain skin's volume. Basically anything that corrects or changes the way the skin moves with our joints is going to have a performance cost associated with it. So those inputs, the joint hierarchy and the skin deformations, are what we're going to input into the machine learning process. And by training it over a wide range of motion, we're going to be able to learn all of those deformation effects and then collapse them down to that single machine learning node that's going to handle all of the skin deformations. So this is a typical use of machine learning as an optimization step in our character publishing pipeline. And we see that used in multiple studios in the industry. So we can take a character rig made the way we normally make it, use machine learning to optimize it, and then it's going to be faster. But as a character artist, that kind of leads to a bit of a light bulb moment when you start to think about, if we can machine learn any type of deformation, then, and we don't have to worry about the performance cost of those deformations, then maybe there's a way to kind of deform our character that really harnesses the power of machine learning so that our characters can be faster and more performant, but also maybe look better on screen. And that's a little bit about what we're going to talk about today. So we're not going to get hung up too much on the machine learning aspect. Instead, we're going to talk about how we would create that rich deformation system that we would feed to a system like that. And for that, we're going to use ZivaVFX. So ZivaVFX is another tool that Unity has, which is for simulation, for character simulation, and it works as a Maya plugin. So with it, you can duplicate and replicate the effects of kind of physics through muscles and soft tissue like this. So you'd start out with an anatomically correct skeleton, build a bunch of muscle objects on top, build out all the material properties, attach those tissues together, and then simulate them along with the skin to get these kind of really super realistic and awesome deformation effects in the mesh. That's where we see kind of muscles and bones slide each other underneath the skin. So today, though, we're going to look at the opposite end of the spectrum with a stylized character and a stylized simulation build. So with characters like these, those type of microforms and detailed muscle effects are usually seen as distracting, and they don't match the sort of design language of the project. So what does it mean to apply simulation to a stylized character? So first off, we're going to have different goals, and those are going to be pretty basic. We want to keep the forms really simple. We want to have clear silhouettes, and we want to have clean lines. And secondly, we want to kind of define what we want to get out of the project. So with the simulatable deformation system, we're going to be able to add automation. We're going to raise the base level of deformation quality. And we're going to improve the character artist's workflow by giving them this kind of really appealing, believable, high-fidelity base set of deformations that they can work on top of to add targeted art direction instead of having to hand sculpt tons and tons of correctives and hopefully end up with a better character on screen. So let's take a quick look at an overview of the process. So we'd start with the control rig, and here I've used M-Gear to make this. Then we'd build and bind our bone geometry into the rig. And the tissues are what we simulate, and they're driven by the bones. But the deformation of those tissues is going to be controlled completely by the simulation. So then we'd use a simple Maya wrap deformer to attach our character geometry to our tissue objects so they all deform together. And once that's completed, we can start to kind of harvest that data. And obviously, the best way to do that is to do some machine learning process. And that way, we're going to be able to take full advantage of this kind of simulation system. And we get a seemingly infinite amount of corrective shapes and combination correctives that we can take out of it. But if your studio is not using machine learning yet, you can still extract shapes by hand and input them into a post-based deformer system. And if you've got a system like that, it's actually going to work really well because all of the shapes that you take out of the simulation were made from one system with one set of rules. So when you put them back together again in a post-based deforming system, you know that the transitions between those shapes are going to line up and the features and forms are also going to line up. So there's different ways you can leverage this technique. So simulation is really good at replicating something from the real world. And if we were creating a realistic human, we would use a realistic human as our reference. For the stylized character, I decided that a stop-motion puppet is kind of the real-world counterpart that I will try to replicate with the technique. So let's go in and look at some of the simulation inputs. So here you can see the bone geometry, and those are the inputs that drive our simulation. And I modeled them from really simple primitives here. It's just a bunch of cylinders, mostly. And you can see I've taken some liberties with the bone design, leaving some kind of larger gaps at the connection points. And that's going to let us increase the range that the character can move when we get to the simulation stage. There's also some floating bone caps on the elbows and knees. And that's just another way to let us kind of control the silhouette of the character. And we'll get into that in a second. So the tissues are what we simulate, and they're driven by our bone geometry, but their deformation is going to be controlled entirely from the simulation. So they're geometry inputs, and we can give them material properties, and that's how we define how they're going to react to the different deformations. And you can see here I've kind of segmented the layout of the tissues, and that's not necessary. It's just for the workflow. If you're going to make edits, if you want to turn off pieces of the simulation to make it run faster, if you want to manage the simulation components, it kind of helps to have it broken down in a modular fashion. If you decide the character is going to have 5 fingers instead of 3, you can swap out the hand and do things like that. So if we look inside, we can see that the tissue objects are kind of modeled to be hollowed out and fit around the bones. And it's important that we do that really cleanly, and we want to avoid collisions. And if we chop it in half here, we can see how they're assembled on the right. And a common question that we get is how thick should the tissues be and how thick should the bones be? So if we think about, if you just had a cylinder, you could put a really thin set of bones in the middle. And then when you deform those bones, the simulation is going to control most of what the deformation looks like. Whereas if you had really thick bones in the middle and a thin layer of tissue on the outside, then the bones are going to be responsible for most of what the simulation looks like in the end. So what we really want to do is make our bones thick enough that we can get a sense of structure, but not so thick that when we deform them, we feel like they would need corrections. The whole point of this technique is to not do a lot of hand sculpting. So we want to keep something like the spine, which is going to be bound to our character, thin enough so that it can deform nicely without needing corrective shapes. So at this point, we want to kind of build out those bones, bind them into our rig, and that's pretty fast because it's just a bunch of cylinders, but it's also an iterative process. So you will want to go back, maybe modify the bones, modify the tissues, test the simulation, and go back and forth a few times to make sure that you've tried all the things you need to try. Which kind of brings us to the simulation. And you can see here we've got the tet mesh, which is what deforms our tissues. You can see in red there some of the attachments made that are kind of stitching together all the tissue objects and attaching our tissues to the bones. And one thing to kind of mention right from the start, is that we'll be using the quasi-static integrator from ZivaVFX to do these simulations. And that sounds kind of complicated, but it's not that bad. I asked Cheng Dong, the ZivaVFX developer back at Unity, to help me explain it. And he said something really interesting. He said, like stop motion, each step of the simulation is solved to the equilibrium state, which I thought was a really interesting way to describe it. So basically, when we run the simulation, we're going to be solving for the deformation, but not for the secondary effects like muscle jiggling and all those type of things. That stuff is going to throw off machine learning, or if we were going to extract shapes, it's going to give us unclean shape data. So this way, we can just set the simulation going, and we know that that data is going to be useful for us later on. So let's look at the simulation in action here. So we've got the leg rotating about 130 degrees. And we're getting a lot of heavy deformation happening around the pelvis tissue. And we can see here that the deformation's holding up, but we're also getting that sense of structure maintained, and we're keeping a nice, really clean form. We're getting proper collisions. We're getting clean geometry. And you can see here a little bit about how the gaps in our bone armature are kind of helping extend the range. So by keeping the top of the leg further away from the spine, we're giving the simulation more room to work and kind of solve for that area of the character. And we can also see here that deformations happening on the lower half of our character are pushing all the way up through the torso in a kind of natural, organic way. So those kind of broad fall-offs are what we're hoping to get from the simulated result. Here we've got the knee rotating 125 degrees with some interesting collisions and compressions happening in the back. And we can see here we're getting that sense of structure again, which is giving us that kind of physically correct feeling, even though we don't have a ton of complicated tissue or bone setups inside. We're also getting a lot of subtlety in the deformations. So even at the minimal rotations, we can see a nice sharp crease line forming in the back of the knee, all the way up from the beginning through to the end of the motion. We can also see the bone design here on the right kind of doing its work. So we've shortened the sections of the knee just to give the simulation more room to kind of solve for that knee area. And then I've added the bone caps on the outside as a way to kind of art direct the form a little bit. So in motion, we can start to see some of our original goals coming through that match the style we're trying to hit. So we've got those simple forms, we've got the clean lines and silhouettes, and we're getting that really nice volume preservation. But we can also see some of the other things that we're aiming for. So that feeling of physicality, a broad deformation fall-off, and that really nice, super clean, deformed surface, especially around the highest deforming areas like the leg here. So the rest of the body is sort of made up in the same way, but the hands are a little bit different. So let's take a closer look at those. So the hands of our character are really short and thick, which makes for a really difficult use case. And I want to match the style and hopefully get that same soft, squishy feeling when we pose the hand. So for the bone design, I've kind of split it into two main sections here. We've got the palm, and we've got the fingers, and I've included a little bit of a nub on the end of each finger, which is going to sort of act as an anchor point for the base of the finger. And then we just have a floating bone tip, and we're going to let the simulation solve for everything in between. And let's take a look at that in a few poses. So here we can see how the bones influence the tissues and how it looks like moving. We can also see the tet mesh here, where I've painted some maps to increase the resolution in a few of the high detail areas. And we can also see, if I can use the mouse here, right in the middle of the palm, there's a really small attachment around here. I think it's right here. Yeah, this one. So, you know, those crease lines in the palm are some of the defining characteristics of what make a hand look like a hand. And when we deform the hand and it puffs up with that volume, we don't want to wash out some of those crease lines. So at the start, I talked about not wanting to do a lot of hand sculpting and corrections on the simulation, but that doesn't mean we don't want to art direct the result. And adding little attachments and things like this are one of the ways that we can do that. So here's a great pose that shows the volume buildup by compression. And so you can see the entire hand changes shape as the fist tightens. And from the front, we're getting that really nice kind of cartoony fist ball. And from the side, we're getting this a really nice, strong silhouette profile. So here's a few examples of something interesting, which is finger-to-finger collisions. It's the type of stuff that you normally maybe wouldn't put into a character rig. But it's nice to be able to do that. And so here, instead of increasing the tet mesh resolution to capture some of this detail, I've shrunken the bones down a little bit. I think the temp mesh is already small enough that we don't want to increase the resolution anymore. So by decreasing the bone size, I can keep the pets the same size that they are now, and they just have a little bit more room to work. So if you're using a post-based deformer system and you want to try and harvest these types of shapes, it's obviously going to be a little bit more complicated because you have to try and drive those shapes. So if you were using that technique, I'd say you could take a few of your iconic kind of hand poses, solve them, and then use that as a one-off shape when you're in those hand poses. Conversely, if you're using machine learning, you could potentially learn all of these types of detailed kind of finger-to-finger interactions throughout the character. And when you do that machine learning process, it also learns how to drive all the shapes. So you don't have to really worry about that part of it at all, provided you had enough training data to show the Ziva RT. So here we can kind of see how the poses of the hand affect the rest of the character, and we're getting a really nice connection between the fingers, the palm, the wrist, and in the arm. So when the wrist rotates down, we can see the thumb and finger pads keeping their shape, pushing into the wrist, and then the wrist pushes back into the arm, and that travels all the way up into the elbow. So it's that kind of really broad and subtle deformation effects that we want to leverage the simulation for and not have to have a character artist painting tons and tons of complicated shapes across a character that are hard to edit later on. So here we got the calisthenic of the entire hand, and we can see the performance over a wide range of motion. And we're getting that nice volume preservation, some of the appealing shapes coming through, and then they're in the same soft kind of round style of the character design. So looking back at the whole simulation build, the component count is quite manageable, as is the simulation time at about 20 seconds per frame for the full body, which means that we can iterate pretty easily on the design while we're working and do those simulations locally. We're also using the quasi-static integrator, which by default kind of increases the speed of the simulation by about 30%. And with the modular design, we can, if you're working on the hand, let's say, you can turn off all the simulation effects on everything but say maybe the arm and the chest. And the simulation speed goes up to about 2 or 3 frames per second. So you can really do a lot of iterating and work on the design of your simulation that way pretty easily. And if you've got longer animations that are taking longer, you can send those to the farm to render out with ZivaVFX in batch mode. So to recap kind of what we've gone over today, we want to take simulation from the end of the character pipeline, and we want to move it to the start of the character pipeline. We want to use it to kind of generate all of our character deformations, and that's going to become a kind of a library for how our character moves. And at that point, we can start to harvest that data, either by machine learning or by extracting shapes to a post-based deformer system. And once that shape data is in the rig, everyone gets to benefit from the result. So materials, grooming, and cloth get this really nice deformed surface to work with. Rigging and the character rig itself get a lot of benefits that we've looked at already today. I think one of the standouts there is that a character artist gets to spend more time doing art direction and less time kind of fixing the basics of how a character moves. And animation is going to get an asset with a higher fidelity deformation with more corrective shapes that work really nice as a cohesive system together. And then if we pair this with machine learning, we're going to get sort of film quality, high quality deformations that can run in real time that are really, really good for games. So that's pretty much it. Thanks so much. If anyone has any questions, I'd be happy to answer them. But if not, thank you so much.